This video will demonstrate how to perform regression analysis in RapidMiner. Regression analysis is a tool in predictive analytics in data science. Let's have a review first on the basic concepts of linear regression. A linear regression model is represented by this equation, wherein you have a dependent variable y, in which this y must be quantitative. In other words, it is numerical, which is predicted by these predictors, which are x sub 1, x sub 2, up to x sub p. Linear regression is a linear approach to modeling the relationship between a quantitative dependent variable. As I've said, this is the dependent variable, which is quantitative, in other words, numerical, and one or more independent variables represented by x sub 1, x sub 2, up to x sub p. Some of the assumptions in linear regression are as follows. The residuals, which is represented by the error term here, are normally distributed. And there must be no multicollinearity among the independent variables. In other words, x sub 1, x sub 2, up to x sub p must not be dependent with each other. Suppose we want to model the effect of weight and sex to systolic blood pressure. In other words, your predictors are x sub 1, which will represent weight, x sub 2, which represents sex. They will predict the systolic blood pressure, which is the dependent variable here. Note that the systolic blood pressure here is numerical form, because again, y here must be quantitative. Thus, our linear regression model is y, which is the systolic blood pressure, is equal to beta sub 0 hat plus beta sub 1 hat times weight plus beta sub 2 hat times sex plus the error term. Given this regression model, suppose that these coefficients were estimated. Let's assume that beta hat sub 0 is 72.4, beta hat sub 1 is 1.02, and beta sub 2 hat, which is 3.23. Note that these are estimates, that's why they are represented with a hat symbol here. Now, since beta sub 0 hat is 72.4, beta sub 1 hat is 1.02, and beta sub 2 hat is 3.23, thus our regression model is 72.4 plus 1.02 times weight plus 3.23 times sex will give us an estimate of the systolic blood pressure. Note that, again, this has a hat because it is an estimate. Remember that in algebra, our linear equation is y equals mx plus b. This is the y-intercept, which takes the role of beta sub 0 hat, and whatever is the coefficient of x, in this case this one, beta sub 1 hat and beta sub 2 hat are slopes. Now, given this linear regression model for systolic blood pressure, how are we going to estimate the systolic blood pressure of a male individual whose weight is 49 kilograms? In other words, the value of the weight here is 49, and the value of sex here, since this is male, that will be 1. So this is 49 kilograms and this is 1. So substituting those values, we have 125.61 millimeters of mercury. How about if we're asked to estimate the systolic blood pressure of a male individual whose weight is 50 kilograms? So in other words, this will now be 50 kilograms and the sex would still be, since this is male, this would still be 1. So our estimate for systolic blood pressure is 126.63 millimeters of mercury. Now, notice here that from 125.61 to 126.63, the estimate of the systolic blood pressure increased by 1.02 millimeters of mercury. Thus, we can say that when weight is increased by 1 kilo, keeping the sex fixed, the systolic blood pressure will increase by 1.02. So keeping the sex fixed, for every 1 kilogram increase in weight, systolic blood pressure increases at an average by 1.02 millimeters of mercury. Next, suppose you're asked now to estimate the systolic blood pressure of a female individual whose weight is 50 kilograms. So in other words, the weight would still be 50, but this time the sex, since this is a female, the sex now will be 0. So substituting those values, we have an estimate of systolic blood pressure which is 123.40. Now notice here that the weight is constant, which is 50. When the value of sex was increased from 0 to 1, in other words, when you compare female to male, from female to male, the systolic blood pressure will increase at an estimate of 3.23. So keeping weight as constant, males at an average have systolic blood pressure that is 3.23 millimeters of mercury higher as compared to females. Now, given our finding a while ago that keeping the sex fixed, 1 kilogram increase will increase the systolic blood pressure by 1.02. That is represented by the coefficient here. Similarly, keeping the weight constant, males at an average have systolic blood pressure which is 3.23 millimeters of mercury higher as compared to female. So in the coefficients here is the effect when you change this value up by 1 unit. So 1 kilogram increase of weight leads to an increase of 1.02 in the systolic blood pressure. Increasing the value from 0 to 1, in other words, you're referring to males compared to females. Males have 3.23 millimeters of mercury higher as compared to female. Again, these coefficients are the changes in the systolic blood pressure when you change these values up by 1. Let's proceed with other examples. How would you interpret now the coefficients of this linear regression model wherein the dependent variable now is HbA1c, which is a measure of glucose in blood? The higher the HbA1c, most likely the individual is diabetic. Suppose the predictors are heart rate in beats per minute, age which is in years, and family history. 1 means the individual has family history of diabetes, and 0 means the individual has no family history of diabetes. So again, increasing this by 1, keeping everything here in constant, will increase the HbA1c by 0.4. Again, keeping age constant and family history fixed, for every 1 beat per minute increase in the heart rate, HbA1c at an average increases by 0.4%. How about age? So again, increasing this by 1, meaning for every 1 year increase in age, HbA1c at an average will increase by 0.6%. Keeping this constant and keeping this fixed. Lastly, for family history, so again, increasing this by 1, so meaning you're referring to those with family history, increases the HbA1c by 1.3%, keeping this constants. So in other words, keeping heart rate and age constants, those who have family history of diabetes at an average have HbA1c that is 1.3% higher as compared to those with no family history of diabetes. Let's have another one. This one predicts cholesterol in milligrams per deciliter this is your linear regression model. Again, since this is linear regression, I want to emphasize that your dependent variable is a quantitative variable. In other words, it is numerical. So let's proceed. How would you interpret daily exercise, which is negative 0.7? So increasing this by 1, in other words, keeping this fixed and this 1, for every 1 hour increase in daily exercise, cholesterol level at an average, since this is negative, it decreases by 0.7 milligrams per deciliter. How would you interpret smoking? 1 means it's a smoker, 0 means it's a non-smoker. Keeping daily exercise constant and race fixed, smokers at an average have cholesterol level that is 8.1 milligrams per deciliter higher as compared to non-smokers. Now, how would you interpret race? As I've said a while ago, increasing this by 1 will change this, your dependent variable, by this. So as it increased by 1, this one increases by 1.3. I'm using the code 0 for Asian, 1 for Black, 2 for White, 3 for Hispanic. Can you say that when Asians are turned to Black, is that it? Or from White becoming Hispanic? It's not. The thing is, when you are working with a categorical variable with more than 2 outcomes, the interpretation of 1.3 is not valid because you cannot increase race by 1 unit. You cannot compare Hispanic with White, Black, and Asian all at the same time using 1.3. It's not. 1.3 is not interpretable. Or basically, this is an incorrect model. So what do we do now? This time, we have to have what we call dummy variables. Now, what are dummy variables? Dummy variables are simply artificial categorical attributes used when the attribute has 2 or more levels. In this case, the categorical variable here has 4 levels or 4 possible responses. That's why we have to consider now dummy variables. What do we do? Suppose this is the data. You have the cholesterol, daily exercise, smoking, and race. You may not proceed with linear regression here since race here is a categorical data with 2 or more levels. So how do we perform dummy variables? Dummy variables would indicate that each possible response here will be a unique variable. There will be a separate attribute for Asians, for Black, for White, and for Hispanic. So this will now be separate attributes. If the race is Asian, Asian will be 1, everything here will be 0. If the race is Black, 1 is Black, Asian will be 0, 1 will be Black, White and Hispanic will be 0. So same goes for this one. Next, since 2 refers to White, so this one is a White individual, then this 2 will be 0, White will be 1. And in this case, we have 3, Hispanic. So these 3 attributes will be 0 and this will be 1. So that will be your dummy variables for the attribute which is race. Now, since these 4 attributes already represent this 1, we may now disregard the attribute which is race. However, an assumption of linear regression is that there must be no multicollinearity among the independent variables. These 6 predictors must not be correlated or must not be dependent with each other. Daily exercise has nothing to do with being Asian, Black, White, or Hispanic. Smoking doesn't have to do with any of this. So we're free with these 2 variables. However, when we refer to the dummy variables, these 4 are dependent on each other. Because your response here would depend if these 3 are 0. This is 1 because these 3 are 0. This is 1 because these 3 are 0. The response in any of these attributes on race would dependent on the response on one dummy variable. So what do we do now? Simply, we're just going to remove one of them to make it independent with each other. The response here would not solely depend on these two. Likewise, the value here does not solely depend on these two. That makes these three independent on each other already. So meaning, when you include a dummy variable with 4 outcomes, you're only going to include 3. So meaning, when you have, let's say, 5 responses in a categorical variable, you're only going to include 4 dummy variables. If you have 6 levels in a categorical attribute, you're only going to include 5 dummy variables. So if you have D levels in a categorical attribute, you're only going to include D minus 1 dummy variables. Actually, when you take a look at smoking, we may have smoking here and another column for non-smoking. If this is 1, this is 0. If this is 0, this is 1. If this is 0, this is 1. If this is 1, this is 0. They are dependent on each other. That's why we do not display it anymore. So in this case, you have 2 levels of this categorical variable, but we only include one of them. Now let's proceed. Since we are sure that there's no multicollinearity anymore, we may proceed with a regression analysis by using only this data. Now, suppose you run now the regression analysis using this data. Suppose this is now the regression model. So how would you interpret negative 0.7 in daily exercise? It means that increasing the daily exercise by 1 hour would decrease the cholesterol level by 0.7 milligrams per deciliter, keeping other attributes constant. How would you interpret smoking status, which is 8.1? From 0 to 1, comparing smoker and non-smoker, smokers have cholesterol level which is 8.1 milligrams per deciliter higher as compared to non-smokers. Again, keeping any other attribute constant. Now, regarding these dummy variables, it's easier now to interpret. Take a look at this one. How would we interpret 0.2 in race black? So you're going to compare 0 to 1. You're comparing black only to Asian. This indicates that individuals with black race have 0.2 milligrams per deciliter cholesterol higher as compared to Asian. How would we interpret 0.7 for race white? It means that, again, comparing 0 to 1, white individuals have cholesterol level that's higher than 0.7 compared to Asian. And then the last one, you're comparing Asian to Hispanic. 1.5 indicates that Hispanic individuals have 1.5 milligrams per deciliter higher as compared to Asian. So it's easier now to interpret coefficients for categorical variables when you have a dummy variable. Now the question is, does multicollinearity exist in numerical predictors? Yes, when you have two numerical attributes which are dependent on each other. Two or more variables are strongly correlated. That is, when one increases, one would also increase. When one increases, the other one would decrease. Things like that. Now, when does it happen? Suppose you have the data cholesterol, daily exercise, smoking, race. Then let's say you add number of gym hours or the number of hours in a gym. What's the tendency now? The number of hours of daily exercise would be dependent on the number of hours in the gym. because counting the number of hours in a gym would also be included in the number of hours in daily exercise. In other words, these two are strongly correlated. Because again, when this one increases, this would also increase. We are sure about that. So now what do we do? Do not include this one. Or if you're doubtful, do not also include this one because they are strongly correlated. Okay? So given these two, if you're going to be asked, should I add gym hours? No, you should not because that is already represented by the daily exercise. Now, what we just like to emphasize here is that when you have a categorical attribute having two or more levels or two or more outcomes, there's a need for dummy variables. And multicollinearity might exist not only if you have a categorical attribute with more than two outcomes, it may also happen with numerical predictors. So later on, in the example, you will know why there's a need to add dummy variables, why correlated variables or dependent variables must be deleted, things like that. Typically, in a statistics class, you have a data, and what do? You analyze it right away. You do not do some partitions or whatever. You analyze it using the full data. Let's say there are 10,000 sample size. You analyze all those 10,000. Now, in data science, we do not use all of this. The entire data will not be used right away. What they do is that they split the data into two partitions. They call it as the training and testing data set, which is usually 80% of the entire data. Some use 70, some use 90, but it's recommended that it's 80%. So what does the training and testing data set do? Or what do they do in that 80%? It's simply to build a model. So you have a data, let's say sex, weight, and systolic blood pressure. You build a regression model out of it. Then measure its some kind of accuracy. Now, what do they do with the other percentage? The other percentage, which is 20% of the data, will be used for validation. So using the same model built in the training and data set, that model will further be validated. So the same model will be used on the 20% of the data. So the concern now here is the accuracy of the model. So I'll show you now what this error term stands for. So the error term in the linear regression model, using the same example a while ago, wherein we're estimating the systolic blood pressure using weight and sex. So we've learned that if the male individual has weight of 40 kilos, it's estimated that the systolic blood pressure is 125.61. So for a male individual whose weight is 49 kilos, the expected systolic blood pressure is 125.61. Then we estimated the male individual whose weight is supposed 50 kilos. So male individual whose weight is 50 kilos. We estimated it's 126.63. And then for a female whose weight is 50 kilos, we estimated it to be 123.40. So these now are the estimates of the systolic blood pressure given sex and weight. Now, is this accurate? That's the question. Okay? Remember, in actual data, we have the data of the systolic blood pressure. These three attributes were used to build this model. Now, how close is the estimate or the predicted value with the actual value? That is now the error term. So it's estimated to be 125.61 using this one. But you have to add 4.39 to come up with the actual value, which is 130. Likewise, for a male, which is 50 kilos in weight, the estimated value is 126.63. But 126.63 is just this one. We have to add 1.37 to come up with the actual value, which is 1.28. Likewise, for female whose weight is 50 kilos, the predicted systolic blood pressure is 123.4, which is represented by this one. But this time, it exceeds 3.40. So you have to subtract 3.40 to come up with the actual value. Note that since systolic blood pressure here is not having a hat symbol unlike this one, meaning this is a predicted value. This one is the actual value. So how close your predicted value and the actual value is measured by the error. Statistically, these are called as the residuals, okay, which is represented by the error term here. The closer the values between the predicted and the actual value, the more accurate the model is. So, in other words, we want this error to be as close to zero. Okay? The lower the value or the closer to zero it is, the better. Now, other analysts consider only the absolute value. So, they do not consider the negative value. That's why they have what we call the absolute error. However, absolute error is relative to the unit of measurement. Okay, so what do? They convert the absolute error with respect to the original value or the actual value. So, they divide it by the actual value. So, in other words, 4.39 was divided by 130, 1.37 was divided by 128, and so on. And you now have a percentage error. So this 3 here is percentage. So since basically these are errors, we want those errors to be very close to zero. Okay, so we want that to be the lower, the better. Other analysts, on the other hand, use squared error. It's simply the square of these values. So meaning they do not want to get the absolute value and the percentage error. So what they do is they square the error so that it will become positive. So these are the squares of these errors here. So what do they do with the squared error? They get the average. That's why there's what we call the mean squared error. And then, whatever's the average, note that since that's the square, the unit of measurement is squared. So meaning, systolic blood pressure is millimeters of mercury, the mean squared error is millimeters of mercury squared. So to get rid of the square, they simply get its square root, so that the unit of measurement will be maintained. So in that case, would still have millimeters of mercury as the unit of root mean squared error. So when we say root mean squared error, it's simply these errors being averaged, after that, taken its square root. Okay, so that is root mean squared error. Essentially, all of these are measures of error. And we don't want a model which has a lot of error. So basically, just to interpret errors later, all you need to consider is that the lower the error, the more accurate the model is. Next, sometimes the data is incomplete. When we say incomplete, suppose we have a dependent variable which does not contain the value of the dependent variable. So, in that case, we have an example data set. So, an example set or an example data set is simply a part of the whole data set which is not part in the splitting process. They were set aside, but it will be used further to estimate the dependent variable. Now, given those background concepts, we may now perform regression analysis using RapidMiner. We're going to use the file which is facebook.xls data. You may download it using the description box below. The Facebook.xls data contains 2014 performance metrics of related posts published in 2014 on the Facebook page of renowned cosmetics brand. So let's take a look at the data. First, import that data using the import data button on RapidMiner. So let's try to observe the data first. So on the first attribute, we have the page total likes on a particular observation time. We have the type, whether the page has posted a photo, a status, a link, or a video. On the third attribute, we have paid, whether the posted medium is paid or not, 0 for not, and 1 if it is paid. And then we have the lifetime post total reach, the lifetime post total impressions. We can also see the number of comments on a particular post, the number of likes, the number of shares, and the total interactions. So most of these are numerical, but type and paid are categorical. However, notice that paid is 0 and 1 and it was categorized by RapidMiner as integer. So we have to set that first to a polynomial. Then click next. Now, among the attributes of the Facebook.xls data, an attribute there, which is the total interactions, will be our dependent attribute. In other words, that will be the one that will be estimated using the given set of predictors. Now, let's prepare the data for the regression model. First is, in the design view, drag the Facebook data to the canvas. Next, let's connect the out port to the rest port. Next, let's use a sub-process operator by dragging it to the canvas. This will enable us some of the processes to be performed inside the sub-process. Next, let's go inside the sub-process operator by double-clicking the sub-process operator. Now, let's prepare now the data for the regression model. First, connect the in and out ports in the sub-process. This will enable us the prior processes and whatever is the processes here be continuous. Next, let's use the set role operator choose total interactions as the attribute name and select label as target role in the parameters tab. So this will enable us to declare the total interactions as the dependent variable. Next, we're going to convert some categorical or what we call nominal attributes to numerical. So using the nominal to numerical operator, in its parameter tab, select subset in the attribute filter type. Select dummy coding in the coding type. And you may check use underscore in name. And type paid and type in the selected attribute. Then click apply. So in other words, paid and type here are categorical predictors or categorical variables. So suppose we have the variable paid and type. Paid has responses 0 and 1. wherein type has possible responses like video, link, photos, whatever. Okay, these are the type of materials uploaded at the page. What RapidMiner will be doing is that this will be converted to dummy variables like type underscore video, type underscore link, type underscore photo, and so on. Next, use the select attributes operator. Then in the parameters tab, select subset in the attribute filter type. And click select attributes. Next, select paid underscore 0 and type underscore video as the selected attributes. Click apply. Next, check invert selection. So this will consider paid 0 and type video among the dummy variables which will be deleted. This will be deleted because they will serve later as the reference. Meaning if this is your data for paid and type, this will be maintained and this will be removed, meaning this is your 0 and this is your 1. In the type attribute, this will be 0 and the attributes here will be 1 because they will serve as the dummy variables. Next, for the numerical predictors, we're going to make use of remove correlated attributes operator. Set greater than 0.9 as the correlation filter relation of the parameters tab. This will remove any pair of attributes with correlation coefficient greater than 0.9 because greater than 0.9 indicates a very strong correlation between two attributes. Next, with the missing values, we're going to make use of the filter examples operator. In the parameter, select custom filters in the condition class. Then click add filters. Locate total interactions in the attributes and set it to is not missing. Then click OK. This tells RapidMiner that if the total interactions is not missing, it will be part of the 80% testing and training dataset, while 20% of this data will be part of the validation process. Now, if the total interaction is missing, it will now be part of the example dataset. Next, for the missing values in X, using the replace missing values operator, select attribute filter type to all and set the default to average in the parameters tab. So this tells the RapidMiner that if you had one attribute, let's say likes, and then there's a missing value, whatever is the average of the non-missing values will be put in the missing values. Connect the unmatched port, which is UNM, of the filter examples operator to the out port. So recapping what we did so far, so you set the role of the total interactions to Y. Next, any nominal attribute was converted to numerical. Next, the select attribute removed some dummy variable, in that case the paid underscore 0 and the type, which is video. We also removed some correlated attributes. So in other words, this prevents multicollinearity. Next on the filter examples, we had the total interactions that if it has values, then we're going to proceed here. If it doesn't have a value, it will be going to this output port. Now for the replace missing values, this is for the predictors. That is when missing, it will just be averaged and imputed to the dataset. Next, go out of the sub-process by clicking the arrow up of the process. We may click play to see what the data looks so far. Now the data so far looks like this. The total interactions has been declared as the dependent variable using the set role operator. Dummy variables was now considered, so we have here photo, status, and link. The type underscore video has been removed because video will serve as the reference. Regarding paid, it has 0 and 1. Only paid underscore 1 has been maintained because paid underscore 0 will also serve as the reference. The other attributes here are numerical. We are sure that none of these attributes are correlated with each other since that is done by the remove correlated attributes operator. Now moving on, we're now going to proceed with splitting the data. Using the split data operator, select stratified sampling as the sampling type in the parameters tab. Now the stratified sampling here ensures that the local random seed would make sure that we have the same split every time we run the data. Next, click Edit Enumeration in the partitions. And let's use 0.8 and 0.2 ratio. So click Add Entry, put 0.8, click Add Entry again, then put 0.2. So again, this indicates that 80% of the data will be used for training and testing, while 20% of the data will go to the validation dataset. Then click OK. Next, we're going to set the optimization parameter to find the best model on the criteria. So using the optimize parameters grid operator, what the optimize parameter do is to find the best model based on the criteria automatically that can be made out of the dataset. It will give you the performance indicators as the parameter changes. So what the operator do is basically automatically change the parameter settings that you want to experiment and perform the modeling automatically and find the model that gives you the best performance. In the parameters tab, choose fail on error in error handling. Fail error here tells the RapidMiner to stop when an error is detected. Next, double-click the Optimize Parameters grid operator to go in the sub-process. Then using a cross-validation operator, in here we will train the model and test the model for its performance, and we do it repeatedly. So what it does is to randomly divide the data into what we call the number of folds and create a model out of it, excluding an optimized number taken on hold to be used in testing. Connect the following: the input port to example port, meaning the INP and the EXA. Next, connect the model port to model port. Next, connect the port's performance to another performance. Next, connect the example and test ports to the output port. Next, Go inside the cross-validation operator by double-clicking it. Inside the cross-validation is the training process and the testing process. The model will be trained based on the parameter that you set. The training part allows you to set what algorithm that you want the RapidMiner to use, like linear regression, support vector machine, artificial neural network, but in this case, we will use the linear regression. Using the linear regression operator in the training canvas, connect the training port to the training port of the operator. Next, connect the model port of the operator to the model port of the canvas. Now, in the testing canvas, use the apply model operator connect the model port of the canvas to the model port of the operator. Next, connect the test port to the unlabeled port. Next, using the performance regression operator, connect the labeled data ports of the apply model and the performance regression operators. Connect the performance port to another performance port. And connect the example port to the testing port. The testing module will let you test the model that you created from the training. The apply model operator applies the model created using the randomly held data. This model will be tested for the performance. The process will be iteratively done by the RapidMiner, and the best performing model based on the performance will be the result. These are the ones in the parameter tab. We may use the root mean square error, the absolute error, the squared correlation, the prediction average. So what are these for? The lower the error, the more accurate the model is. Next, regarding correlation, the higher the correlation, meaning the closer the squared correlation to 1.0, the better it is. Next, the prediction average, the closer the prediction average with the actual average of the values, in that case the total interactions, the better. Next, go back to the optimize parameter grid sub-process. In the parameters tab of the cross-validation operator, click Edit Parameters Setting. Now this is where the parameter will set what we want to be optimized. Next, select cross-validation. Then transfer the number of folds and sampling type in the selected parameter. Now this part allows you to select the parameter that we want to change. We can select as many parameters that we want to be automatically imputed by the RapidMiner to create a model. Note that if we have more selected parameters, then we will have longer process time because it will perform all the possible combinations. For demo purposes, we just have to use these two parameters that we selected from the cross-validation. Next, remove stratified sampling in the choices below, then click OK. Next, we're now going to proceed with the validation data, and we're going to apply the same regression model. So go back to process, and using the apply model operator. Now this process is the validation stage of the data mining, wherein we will use 20% of the data from the partitioned data in order to perform an evaluation of the model that was created. This will ensure how the model will perform with a new data set. This will also ensure that there will be no overfitting that had happened in the modeling process. When we say overfitting, it is the condition that the model will perform excellently in the given sample, but not when applied to a population data or in another set of samples or in another set of sample data coming from the same population. Connect the model ports from the optimized parameter grid and the apply model operator. Next, connect the parameter port of the split data operator to the unlabeled port of the apply model operator. Next, use the performance regression operator and connect its labeled port. Connect the performance port of the performance regression operator to the results port. So what we have to remember is that once the data has been split into 80 and 20, 80% will go to the training and testing dataset. So this contains the training and testing. Then whatever's the 20% will undergo the same model generated from the training and testing and will be gauged as well. So the criteria of the performance will again be based on the root mean square error, absolute error, squared correlation, and the prediction average. Note here that it is expected, or it's a must, that the performance of the validation dataset, meaning the 20%, must be better than the performance of the testing and training dataset. So this shows that you have 80% data which was used for the training and testing. You have the 20% which is for validation. Now the idea here is that you have a data which is represented by the 80%. And then you model it. Once a new data comes in that is represented by the 20%, you want that same model to be at least as good as the previous result. Or in other words, once you have a new data, you want the model to be at least as good as the previous result. You don't want the model to be performing worse than before. You want the model to be performing at least better than before. So you want the performance of the 20% be at least better than the one in the 80%. We're on the last part. We're going to predict the dependent variable y of the example dataset. So we're on this last part here wherein if y is missing, still we're going to have a predicted value. Now to perform that using another apply model operator, connect the model ports of the apply model 2 and apply model 3 operators. Connect the output port of the sub-process operator to the unlabeled port of the apply model 3 operator. Next, connect the label and model ports of the apply model 3 operator to the results port. So to recap everything that happened, On the sub-process, we were able to declare that the total interactions is the dependent variable. We were able to remove some dummy variables. We were able to eliminate correlated attributes. At the end of the sub-process, it identified whether the actual value of y is present or y is missing. If y is present, the data were split into two, the 80%, which is the testing and training, and the remaining 20%, which is for the validation. Testing and training built the model, and then the same model was applied to the validation dataset. Next, performance was measured here. Likewise, performance of the 20% of the validation data was also performed. Now, if y is missing, it went here and same model was being applied. No need to measure the performance of the example dataset since the actual value in this dataset is missing. Now, click Save and click Play, and you will have these results. We have the linear regression model, the performance vector, the optimized parameter grid, and the example dataset. On the linear regression results, this represents the linear regression model. So we have y, or the total interaction, as 20.139 plus 2.119 times the number of shares plus 1.858 times the number of comments. So remember that, how do we interpret it? For every share, for every 1 unit of share, the total interactions increases by 2.119. For every 1 comment, the total interaction increases by 1.858. So that's how we interpret these coefficients. The same goes for these attributes. Next, this shows the performance of the 80% of data, which is the training and testing data set. So we have a root mean squared error of 29.6, absolute error of 21.49, squared correlation of 0.94, and prediction average of 211.428. Next, the second one, which is the performance vector 2, is the performance using the validation dataset. So we have here a root mean squared error of 29.367, absolute error of 17.7, squared correlation of 0.99, prediction average of 214.89. Now, do they have better performance as compared to the training and testing dataset? Let's compare. This is the result of the training and testing dataset, which is again 80% of the dataset. And this is the result of the validation dataset, which came from the 20% of the dataset. For the root mean squared error, we had 29.6 for the training and testing dataset and 29.367 for the validation dataset, which shows that the performance of the validation dataset with the root mean squared error as the criterion is better than the training and testing dataset. As for the absolute error, we have 21.493 for the training and testing dataset, while 17.746 for the validation dataset. So the absolute error is lower in the validation dataset, which shows that the validation dataset is better than the training and testing dataset using the absolute error as the criterion. And lastly, for the squared correlation, we have 0.941 for the training and testing dataset and 0.990 for the validation dataset. Since the squared correlation of the validation dataset is higher than the squared correlation of the training and testing dataset, it shows that the validation dataset is better than the training and testing dataset when it comes to the squared correlation. So these results show that using these three criteria, the validation dataset performed better as compared to the training and testing dataset. Next on this result shows the result of the example set or the apply model 3, wherein we see that the total interaction is missing, but still the model was able to predict the dependent variable, which is the total interactions. Now the question is linear regression the best model to predict the total interactions or the dependent variable? To answer that, the result here must be compared to other models. So you may try the general linear model, the polynomial regression, the support vector machine, and the neural network. So all you have to do to perform that, you just have to change this operator under the training canvas in the cross-validation subprocess. So you're going to change that to general linear model, then take a look at the performance of the validation dataset, and then try using polynomial regression, and then take a look at the criteria, then take a look at the performance again of the validation dataset, and then use support vector machine, then again take a look at the performance of its validation dataset, and then the neural network. So using linear regression, the generalized linear model, the polynomial regression, the support vector machine, the neural network, which of those 5 would better predict the total interactions? So in behalf of the other professors who are teaching this course, thank you for listening.